Hi, everyone. I'm back. I'm sorry I had to end the class so abruptly last Wednesday. I had a family emergency that actually required me getting on an airplane Wednesday afternoon to Portland, Oregon, and I've been in Portland ever since. You're watching this because I've pre recorded it over the weekend. It's now Saturday, right, as I speak. I was hoping I could be with you, but I pre recorded this just in case I couldn't. And obviously, if you're watching it, then I'm dealing with stuff up in Portland. So I don't want to get into what's going on here. So let's just jump right into class and pick up where we left off. I'll remind you where we left off, and then we will move on from there and try to finish up what we were going to do last Wednesday. I think time-wise, we're going to be okay. Last couple of class sessions, we were going to do some optional topics. So just since we lost today, it just means we'll do one less of those optional topics. And I think we'll be fine. Um, so let's see, let me share my screen here and see if we can get going. Okay, there we go. There's my iPad screen. Let me just remind you of where we were at. We were looking at, I was reminding you about phase lines and first order differential equations and what happens when you have a nonlinear first order differential equation, how you might go ahead and sketch the phase portrait. And then this whole idea of linearization. And then we were just about to get into linearization of systems of differential equations. So let me just very, very quickly remind you um, the, the case for differential equations. So you've got a differential equation like dx dt equals something. You've got just some function of x here. So I'm just going to do this very broadly, very generally. And this function of x might have some graph. So we can plot f of x versus x, and we'll see some picture here. And these points where it crosses the x-axis, those are the places where f of x equals 0. And if f of x equals 0, I'm just going back to the original equation, that means we have 0 up here in the original equation, which means we're at an equilibrium point, right? So these points up down here where we have, sorry, my iPad coming here, these points here and here are going to correspond to equilibrium points, right? So let's say this were at -2 and this were at 1. That means that once I start drawing the phase line, then I know that I have an equilibrium point down here at -2 and an equilibrium point up here at 1. So the question is, what's happening in between those equilibrium points, or more importantly, what's happening near those equilibrium points? That's really what we're trying to get out here with this idea of linearization. So we want to think about really what's happening in a neighborhood of this point. So if I just zoom in on this point right here, it looks like I have a system where this curve going through here is just, if I zoom in enough, that just looks like a straight line. And the slope of that line is exactly the derivative at that point, meaning it's going to be f prime of 1. Now this is going to be the graph of the equation dx dt equals whatever that number is, f prime of 1 times x, right? This is just going to be some number, right? And that number represents the slope of this graph. And if I were to just plot the phase portrait for this little tiny system here, this very simple linear system, I'll see a single equilibrium point, and that looks like a negative slope, which means things are moving toward that equilibrium point at a particular rate. Okay, we're not seeing that rate in this picture, in the phase line picture, but that's important to understand, is that everything's moving toward the equilibrium point at a particular rate. And this is exactly the picture that we're seeing right around the corresponding equilibrium point over here on the right. So there's that equilibrium point over here on the right, okay? And we're saying this is the picture we should be seeing up there around that equilibrium point. So around that equilibrium point, we're seeing things move toward the equilibrium point at a particular rate. The behavior near that equilibrium point is the same as the behavior of the corresponding linear system. Right? So we've linearized the system around that equilibrium point by replacing that system with a simpler system. It's just this very, very simple system right here. It's just a simple linear system. And the key here is the derivative is popping up because the derivative is what's giving you the equation of the linearized system. Okay, and then to really finish the story here, we could also linearize around this point right here, kind of blow that up, and then we'd see a similar sort of picture, but now the slope is going up, and the slope of that is f prime of minus 2, which means if we wanted to model that system, it would look like dx dt equals f prime of minus 2, whatever that number is, just some number, times x. Right? That's going to be a differential, just a simple linear differential equation. It'll have a phase portrait where things are moving away from the origin because in the picture there's a positive slope, which means coming back to this equilibrium point here around minus 2, things look just like this picture down here. So things move away from the origin at the same rate as they did down here. Okay, we're not seeing that rate at which things are moving away from the origin there, but if we were to somehow plot that, we would see the same thing up here. So near the equilibrium point minus 2, the system is behaving like this linearized system, and near the equilibrium point 1, the system is behaving like this linearized system. We can do the exact same thing in 2 dimensions by replacing a 2-dimensional system with a linear 2-dimensional system. A linear system just means it's something times x plus something times y, and those somethings will be the derivatives. So so just to be very clear here, if we have a system, dx dt equals some function of x and y. It's not going to be a linear function of x and y. It's no longer going to be like something times x plus something times y. In general, it would be much more complicated. But we also have dy dt equals some function times x and y. Okay. Then the point is, we might have a few equilibrium points. So we might have equilibrium points at x0, y0, and at x1, y1, etc. Right? Well, I have a whole list of equilibrium points now because it's not a simple linear system anymore. Simple linear system just has a single equilibrium point at the origin. Now we have a nonlinear system that might have multiple equilibrium points. Okay? But what we do is around this equilibrium point here, we're going to linearize the system by looking at a linear system with constant coefficients, and those coefficients are coming from the derivatives, except now we have multiple variables, so we're talking about partial derivatives now. So this whole system is going to get replaced by a different linear system, which will be dx dt equals, I'm going to look at the partial of f with respect to x evaluated at x0, y0. Okay, so that's just all going to be a number, right? Just keep in mind, keep that in your head. That's a number times the variable, times the variable x. Sorry, I'm getting a call. Just decline that. Plus some other number, which is the partial of f with respect to y, evaluated at the same point times y, right? Now, which again, this is just a number. That's a variable. This is another number. That's a variable. Okay, so we have number times x plus number times y. Very simple linear system, the kind of system we spent the last month analyzing. Right? Now that's half the system. The other half is dy dt equals the partial of f, sorry, the partial of g with respect to x at x0, y0 times the variable x plus the partial of g with respect to y at x0, y0 times the variable y. And if we like, we can write that in a more compact form, right? All of that we can write as a matrix times xy, and that matrix is the partial of f with respect to x at x0, y0, partial of f with respect to y at x0, y0, partial of g with respect to x at x0, y0, and partial of g with respect to y at x0, y0. Okay, and again, that's just going to be four numbers. Now, what four numbers those are, you're going to figure out by doing some calculus and taking some derivatives and plugging in some numbers. Okay. In practice, what we'll do, we'll work out an example in a minute, is we'll figure out those derivatives first, and we'll get this matrix where we have four functions. And then once we figure out the equilibrium points, we can plug those coordinates of those equilibrium points into each of these four functions to get a 2x2 matrix of numbers. And that 2x2 matrix of numbers we will analyze just like it were a 2x2 system. Sounds like a lot. I'm talking very fast. Probably sounds like this is going to be completely overwhelming. You just got to do it a couple times and you'll see it's just very, very mechanical. It's just, we're just adding on one layer of complexity on top of the work we've already done. In the end, you're just going to end up analyzing a 2x2 system that you've been analyzing all along. You just may have to do it multiple times now, one for each of the equilibrium points. Okay? Now, the point is that now this more complicated system is going to look like this system, but only around that equilibrium point. Okay? And then it'll look like some other system around another equilibrium point. And it'll look like some other system around some third equilibrium point, etc. Okay, so you'll do that analysis for each equilibrium point, and then you got to put it all together in the end into a final picture. So we'll have the xy plane, we'll have the equilibrium point x0, y0. I should have done that in red. Okay, we'll have the equilibrium point x1, y1, and an equilibrium point, let's say we also have x2, y2, okay? And near each of these points, this nonlinear system will look like the linear system that we will have analyzed, okay? I'm about to do an example, so you'll see this. But what we'll do is we'll draw a little picture. Let's say near x0, y0, it looked like a saddle with certain eigenvalues and eigenvectors. Well, we plot the eigenvalues and the eigenvectors, and if it looks like a saddle, it might be looking like this. Okay, maybe near the blue equilibrium point, it looks like a source, where things are moving away from the origin. Okay, and we can kind of fill in the picture. Oops, I get the idea. Okay, and then maybe near the green equilibrium point, it looks like a center where things are spiraling clockwise. And very, very often, you will find that just knowing what the picture looks like around these equilibrium points is enough to fill in the whole plane, or at least get some sense of what all the points look like. We may not know what things look like very far away from all these equilibrium points, but at least right around these equilibrium points, we can often fill in the rest of the picture in between them. Just like way up top here with the one-dimensional system, once we knew what things look like around this equilibrium point and this equilibrium point, then we can fill in the picture. Things are going up here and up here, then they have to be going up here, and here they're going down, and here they're going up, down. Right, so we know what the whole picture looks like once we know what the picture looks like right around the equilibrium points. So it's a super powerful technique. It's not always enough to be really precise, and we'll see some other techniques that will help us fill in the picture more and more and more. But for now, we'll see that we can work out some examples where we really will get a sense of everything that's going on in the system, okay? So my goal is to work out 2 examples here. And I just realized I don't have a timer going, so I don't know how long I've been talking. So I'll work out both these examples and hopefully it won't be too long. Okay, so let's see. Let me flip over to here to this system that I've worked out. This is this is similar to one of the ones in the book. I'm here in Portland and I left in a hurry, so I didn't grab my differential equations book. I thought I was only going to be here 2 days, but if I'm talking to you right now, it's Monday and I've been here a lot more longer than 2 days. Um, so let's just go ahead and analyze this. Our goal is to first find the equilibrium points, like always, but then we're going to add to that this linearization technique near each equilibrium point, and then we're going to try to reconstruct the picture of the entire system across the whole plane, okay? So let's just get started. To find the equilibrium points, we set both equations equal to 0, okay? So we've got to set 4x minus 2x squared minus xy equal to 0. That's the first equation. And minus 2y plus 2xy equal to 0, right? Now, to have an equilibrium point, both these equations have to be 0 at the same time. I find with students that the hardest part here is the algebra of finding the equilibrium points, not the calculus or the linear algebra or putting it all together. This is the hardest stage right here, is you've got 2 nonlinear equations and they have to both be 0 at the same time. And so there's this logic we'll see. There's really an implicit and between these. I'm even going to write it in, okay? Because we're going to have ands and ors, and if you have taken discrete math especially, you know when you have a logical statement with ands and ors, it can get a little complicated. Let's work on this second equation first. So we can cancel the 2's, just divide everything by 2, and that gives us minus y plus xy equals 0, which I can factor out a y and rewrite this as y times minus 1 plus x equals 0. And that tells us that either y equals 0 or x equals 1, right? So we've got ands and ors going on here. This is exactly what I was saying. All right, now we're trying to find the equilibrium points. So the 2 original equations have to be 0 at the same time. If we're in the situation where y equals 0, and we also know the first equation has to be true, we can combine those, and that gives us 4x minus 2x squared minus x times 0 equals 0. Okay, all right, so let's keep going with that. That's 4x minus 2x squared equals 0. We could divide everything by 2, make it a little simpler, and at the same time, I'll factor out on x. So that's x times 2 minus x equals 0. And that tells us that x equals 0 or x equals 2. Okay, now here's where it gets complicated, right? We've got y equals 0 and x equals 0 or x equals, oops, that was supposed to be 2. 2. Ooh, wrong tool. 2. Okay, so that means we've got now 2 equilibrium points here. We've got x equals 0 and y equals 0. That's 0 comma 0. Or we have x equals 2 and y equals 0. Okay, so far we found 2 equilibrium points. Now we've got to go back up to the top because we missed a case. It could be that the first equation was true and x equals 1, right? Rather than y equals 0, we could have x equals 1. So we have to combine this equation and this equation. And that gives us 4 times 1 minus 2 times 1 squared minus 1 times y equals 0. Okay, simplify. It's 4 minus 2 minus y equals 0. 2 minus y equals 0. Y equals 2, right? So now we're in the situation where x equals 1 and y equals 2. And that gives us the equilibrium point 1 comma 2. Okay, so we found 3 equilibrium points: 0, 0, 2, 0, and 1 comma 2. All right. Now, what we want to do is write down the corresponding linear system near each of those equilibrium points. So we're going to replace the original system with a linear system that corresponds to the partial derivatives. Okay, so again, we've got, let me just make sure you all understand this. So we've got dx dt equals some function of xy, dy dt equals some other function of xy. We're going to replace this with the system dx dt dy dt equals the four partials: partial f with respect to x, partial f with respect to y, partial g with respect to x, partial g with respect to y, x, y. Okay, we're going to evaluate those partials at each of the equilibrium points. Okay, and then there'll just be a 2 by 2 matrix. So let's go ahead and do it. Again, the original system, I'll just copy down again. Dx dt is, let's go back, 4x minus 2x squared minus xy, 4x minus 2x squared minus xy. Okay, and dy dt is minus 2y plus 2xy. Minus 2y plus 2xy. All right, so we're going to replace that with the linear system, dx dt, dy dt equals, and I have to write down a matrix. And the way I'm going to get this matrix is I'm going to compute the four partial derivatives at each of the equilibrium points. So let's do the partial derivatives first, not worry about it being at the equilibrium points, and then we'll plug in those values. So the partial of f with respect to x, I'm differentiating that first equation with respect to x, that gives us 4 minus 4x minus y. The partial of that first equation with respect to y is just minus x. Partial of the second equation with respect to x is just 2y, and the partial with respect to y is minus 2 plus 2x. All right, now those don't look like just numbers because we haven't evaluated them at the critical points. So we have, at the equilibrium points, we have 3 equilibrium points. We found 0, 0, 2, 0, and 1, 2. So we have to plug in 0, 0. What did I say? 2, 0, and 1, 2. And we're going to evaluate that matrix at each of those equilibrium points, and then we'll be back to having a nice 2 by 2 matrix. We'll have 3 of them. We'll analyze the system near those 3 points, and then try to reconstruct the picture of the original system. All right, so if I plug in 0, 0 into this matrix right here, we get 4 minus 0, that's 4. We get 0, we get 0 again, and we get minus 2. See, that's a nice one. I can tell you right now that has eigenvalues of 4 and negative 2. The eigenvector for 4 is 1, 0, and the eigenvector for minus 2 is 0, 1. Right, well, I hardly have to do any work there because it's a nice diagonal matrix. You can just read off everything. All right, for 2, 0, x is 2 and y is 0. So when x is 2, I have in the top left, I have 4 minus 8 minus 0. That sounds like minus 4 to me. Okay. the top right, I have minus x, so nx is 2, so it's minus 2. The bottom left, I have 2y, and y is 0. And the bottom right, I have minus 2 plus 2 times 2. It's minus 2 plus 4, which is 2. Okay. That's called a triangular matrix. I can tell you right now the eigenvalues are minus 4 and 2. I'll work that out in a minute. But I don't know what the eigenvectors are. It's not so easy to figure out the eigenvectors are. You have to actually do the work. We'll do it in a minute. Let's finish up. The equilibrium point 1, 2, x is 1, y is 2. So on the top left, we have 4 minus 4 minus 2. That sounds like 0 minus 2 to me. Top right, we have minus x. X is 1, so we have minus 1. Bottom left, we have 2y, and y is 2, so that's 4. And the bottom right, we have minus 2 plus 2, which is 0. Oh boy. All right. I have no idea what that looks like. All right. So I'm not going to work out the first one. We have, I'll just write down the answer. We have lambda equals 4, and that corresponds to an eigenvector of 1, 0. And lambda equals minus 2. That's going to correspond to an eigenvector of 0, 1. It's just on the x-axis and the y-axis. Okay. For the second one, it's a triangular matrix, so the eigenvalues are minus 4 and 2. You can work that out for yourself. If you don't believe me, just subtract lambda from the diagonal, write down the determinant, that's the characteristic polynomial, and you can work it out. It's a little harder to figure out the eigenvectors, though. You have to actually do some work here. So for lambda equals minus 4, let's write down the eigenvector. I'll just work it out. We have minus 4 minus 2, 0, 2 times xy equals minus 4 times xy. We'll get two equations there. The second of those two equations is 2y equals minus 4y. That tells us that y equals 0, and that tells us that anything for x is an eigenvalue with y equals 0. It's an eigenvector, sorry. So for example, 1, 0 is fine. And that's typical for triangular matrices. The first entry there is, it's just like if you have a diagonal matrix, where the first entry is the eigenvalue and the eigenvector is just 1, 0. It's the second entry where things are a little more complicated, not that much more complicated. For lambda equals 2, now we'll just work it out. Minus 4 minus 2, 0, 2 times xy equals 2 times xy. The second equation is 2y equals 2y. That tells us nothing. So all the information here is in the first equation, which is minus 4x minus 2y equals 2x. Add add 4x to both sides. That gives me minus 2y equals 6x. I don't know, divide by negative 2 gives me y equals minus 3x. And so we get an eigenvector of 1 minus 3. Okay, so for an eigenvalue of minus 4, we have an eigenvector of, or minus 4, we get an eigenvalue of 1, 0. And for 2, we get an eigenvector of 1, 3. All right, last one. Let's write down the characteristic polynomial. We have minus 2. We're going to do the determinant of minus 2 minus lambda, minus 1, 4, and 0 minus lambda. Okay, so let's write down that characteristic polynomial. That's minus 2 minus lambda times minus lambda. A lot of people calling me right now. Minus negative 4 is plus 4 equals 0. So that gives me let's see, I got a lot of negatives here that'll just cancel. That's 2, 2 lambda plus lambda squared plus 4 equals 0. Rewrite that, make it look a little nicer. Lambda squared plus 2 lambda plus 4 equals 0. I don't think that factors, so let's go ahead and jump right into the quadratic formula. That gives us lambda equals minus 2 plus or minus the square root of b squared, that's 4, minus 16 all over 2a, minus 2 plus or minus the square root of minus 8 over 2, minus 2 plus or minus, okay, square root of minus 8, we're going to get an I out, and we have square root of 8 there, which is 2 root 2. Well, that's over 2. The 2's all cancel. That gives us minus 1 plus or minus root 2i. All right. Now, it's funny because previously when we got complex values, it turned into the hardest problem I could ask you. We're going to have to now look at the real value, to find the general solution, you had to look at the real parts of the eigenvectors, and there was quite a bit of work you had to do. But all we're doing at this point is just trying to sketch the graph. And we know what this graph looks like now. Because that minus 1 is there, and the absolute, you look at the absolute value of the real part. If the absolute value of the real part is 1, then it has to be a center tangency. And that's all we need. Okay, as long if the absolute value is less than 1, then it's a, oh, I lied. Why did I lie? I'm sorry. The absolute value, that's, you don't look at the absolute value. I'm talking nonsense. Please, if I could, I would erase the last minute of this video, but just ignore it. It's negative, therefore it is a spiral sink. That's all we gotta know. Okay, it's complex, so it's a spiral source or a spiral sink. If the real part's 0, that's what I meant to say, then it's a center. If the real part's positive, it's a spiral source. If the real part's negative, it's a spiral sink. Sorry, I was not talking correctly. So near the equilibrium point 1, 2, we're going to see a spiral sink because that was the corresponding eigenvalue. Okay, so let's put it all together now. Now it's time to finish this problem. So here we go. I'm going to make some nice big axes. We've got 3 equilibrium points, and I'll try to color code them. So the first one is red. That's 0, 0. And so down here, we've got 0, 0. Okay. And near that equilibrium point, we had 2 eigenvectors. Along the x-axis in the 1, 0 direction, we see a eigenvalue of 4. Okay, so in the 1, 0 direction, we see an eigenvalue of 4. Okay, and 4 is pretty big. And in the 0, 1 direction, we see an eigenvalue of minus 2. So in this direction, we see an eigenvalue of minus 2. So that's a saddle. So things move in around this equilibrium point. Near this equilibrium point, things are moving along these hyperbolas. Okay. All right, next equilibrium point is, we've already color coded it blue, 2, 0. Around 2, 0, let's just plot it for a minute. So 2, 0, let's see. Here's 1, 2, 1, 2. Around 2, 0, 2 over 0 up, that's right over here. That has an eigenvector of 1, 0, where the eigenvalue is negative. So 1, 0, this direction, and the eigenvalue is negative. Negative means things point toward that equilibrium point. And in the 1, minus 3 direction, we have a positive eigenvalue. It's another saddle. Okay, so if I go from this point over 1 and down -3, that's a pretty steep line. And there I have a positive eigenvalue. Okay, so again, now things look like saddles. Just going to fill in the picture now. All right, and then we have one more equilibrium point, this green one. Okay, at 1, 2, I see a spiral sink. Okay, so at 1, 2, that's up here in my picture, I see a spiral sink, and you can already tell from this arrow and this arrow what direction it is. It's worth checking, but I bet you anything it's going to spiral in like that. Okay, now we got to fill in the rest of the picture, and it should be fairly easy to do that. Now, of course, there's no guarantee that this is going to be correct, but usually the simplest thing is the one that works. So what's happening here as we leave this first equilibrium point, we're going to get sucked into that one. Right? So things are moving along the x-axis that way. Somehow over here, things are going to go toward this point. Now, they don't necessarily stay along the y-axis. Maybe things go that way. And same thing, leaving this equilibrium point, what's probably going to happen is we're going to get kind of sucked in to this equilibrium point here. Down here, we've got some curve along which we enter that saddle, and here we've got some curve along which we leave, and then things seem to move like that. Okay, again, I'm just kind of filling in what I can. It's looking to me like the picture is probably something like this. Things are just getting sucked into that equilibrium point. Okay, even from way out here, things will get sucked into that equilibrium point. So it's kind of an awesome picture. It's awesome how just plotting a couple equilibrium points really does let you fill in the picture in a really beautiful way. Super nice how that works. Okay. All right. I think I've been talking about 40 minutes now. So we've got time for one more example. I don't want to completely overload you, but let's work out one more example. I think the next example is actually going to be simpler, and it's a nice modeling example. We've talked about the mass on a spring before, and so now we're going to do something a little bit different, which is the simple undamped pendulum. So we've just got a pendulum like this, and we want to model that behavior. And again, we're just going to use a little tiny bit of basic physics like we did with the spring, with Newton's equations. We'll write down the answer. The hardest part here is just going to be a little bit of trigonometry. And then we'll come up with a 2x2 system. We'll linearize that system around the equilibrium points and can reconstruct the picture. And I think this one is significantly easier to do the linearization. The only hard part is going to be just getting the equations from the physics. So let me draw the picture and we'll just get started here. So we've got this nice simple pendulum of length L. Okay, and some things to know about the pendulum. We've got the force of gravity on it, and from physics, you should know that the force of gravity is F equals mg. G is just the gravitational constant, and m is the mass of the pendulum. Okay, so that force is just constant, right? M is a constant for that bob on the end of the pendulum, and g is the constant. So we've got this constant force pulling us down, and it's pulling us straight down. And since it's down, we're going to say that's negative. It's because it's in the negative direction. Okay. The pendulum, we'll say our pendulum is swinging this way, which means it's moving in this direction. that's accelerating in that direction. And we've got the other one of Newton's laws is F equals ma, mass times acceleration, all right? Now, the problem is these are going in different directions. And in physics, they tell you all your forces have to balance, right? But they have to balance in the same directions. So what we have to do is we have to compute the component of the force of gravity that's acting in direct opposition to the direction of acceleration. So we need the component of the force of gravity. So the way we do that is we draw a little right triangle here, and then we have to say, what is this? Okay, now that's going to depend on a tiny bit of trigonometry. So let's get some angles involved. Typically what we do is we say this angle here is alpha. That means this angle is alpha. And since that's parallel to the one of the sides of the right triangle, we get an alpha here. Okay. Now the hypotenuse is just the length of that arrow, and the length of that arrow is mg. Okay, that's this length right here is mg. So if I want to figure out what this number is, let's call that x for now. I need some trigonometry. I've got the angle alpha, the side opposite that angle, and the hypotenuse. So the relationship between opposite side and hypotenuse is the sine function. So we have sine alpha equals opposite over hypotenuse, which means this number x is mg times the sine of alpha. Okay, mg sine alpha, but again, it's pointing down, so there should be a negative sign here. Okay, so far we have minus mg sine alpha equals the force going in the other direction. Right? We've got this force in this direction, that's minus mg sine alpha, sorry, equals the force going in this direction, which is the mass times the acceleration. All right. Now, acceleration, you know, is second derivative of position. But we've got, on the left, we've got things in terms of the angle, not the position. So what we need to do is get position in terms of angle. Now, this is where the beautiful thing about radian measure. If I have a point on a circle of radius L, then if I move an angle of alpha, then I will have moved on the circumference of the circle L times alpha. And that's exactly what radian measure is it is, if L were 1, then I've been moving, and alpha is 2 radians, then I'm moving 2 times the radius. That's what radians are, okay? But when I increase the circle by a factor of L, then I increase the arc length by a factor of L. That's why we get L alpha instead of just alpha there on the circumference. Okay. So typically the way the physicists write this is they say the length you've traveled, they usually use the letter S for that, is exactly the radius of the circle or the length of the pendulum times the angle. Okay. Now the acceleration is the second derivative of the displacement of the distance traveled along the circle. Okay, L is just a constant, so that's just L times the second derivative of alpha. Okay, so we're going to combine that with this equation, and we get minus mg sine alpha equals m times L times d squared a dt squared. Okay. Interesting thing here, just an observation, is that the m's cancel, and that's actually kind of fascinating. It says that the amount, if you have a mass at the end of a pendulum bob, that the mass doesn't actually matter. A lot of the dynamics, how fast this thing goes back and forth, only depend on the length of the pendulum. They don't depend on the mass of the bob at the bottom. um, which is kind of fascinating. And that's experimentally, that's true. This really mirrors the experimental data really well. All right, let's keep going here. So if we put everything on one side, we get d squared a dt squared plus, no, yes, d squared a dt squared um, equals minus g over L sine alpha. This is the equation we end up getting from the physics. Okay. Sorry, not A, alpha. That should have been an alpha. Sorry, why didn't any of you stop me? This was an alpha. Okay, all right. D squared alpha dt squared equals minus g over L sine alpha. So we have a second order differential equation, and as usual, we're going to turn this into a first order system by introducing another variable. The first derivative of angular displacement is called angular velocity. Angular velocity is just telling you the rate of change of the angle. And I think physicists like to use the Greek letter omega for that, which looks like a lowercase w. So we're going to say d alpha dt equals omega. And then we can rewrite this as the system d alpha dt equals 0 times alpha plus omega, okay, and d omega dt equals minus g over L sine alpha, okay, plus 0 times omega if you want. All right, now we're going to assume that we've picked our constants so that g over L is just 1. So we end up with d alpha dt equals omega, and d omega dt equals minus sine alpha. And all that physics, and we got down to a much simpler equation than we got before. So let's now do the whole linearization technique. We're going to find the equilibrium points by setting both these equal to 0 simultaneously, and then linearize the system around each equilibrium point, and then we'll call it a day. Okay, so we want to set omega equal to 0 and minus sine alpha equal to 0. That tells us sine alpha equals 0, and that tells us that alpha equals 0 or any multiple of pi. All right, so putting these together, we have really any multiple of pi, 0, 1 pi, 2 pi, 3 pi, minus pi, comma, 0. That's alpha comma omega. All right, now let's linearize our system. We're going to take this system, we're going to rewrite it with a matrix of partial derivatives and look at the values of those partial derivatives at each of the equilibrium points. Okay, so here we go. We are doing d alpha dt and d omega dt equals this linear system times alpha omega. And to get the linear system, I've got to first take the partial of the first function with respect to alpha, that's 0. Then I take the partial of this first function with respect to omega, 1. Then the partial of the second function with respect to alpha. So I have the derivative of negative sine, which is, well, the derivative of sine is cosine, so I have minus cosine alpha. And then the derivative with respect to omega, which is 0. All right, let's keep going here. Now I'm going to evaluate this at all the multiples of pi. Okay, now it turns out there's only two possible values. If you remember what the graph of minus cosine looks like, just for a second, I'll just do this as an aside. The graph of cosine looks like this, which means the graph of color here minus cosine looks like this. Okay, so it alternates between minus 1, 1, minus 1, 1. So on the even multiples of pi, we get negative 1. And on the odd multiples of pi, we get 1. Okay, so this matrix right here is either, let's see, 0, 1, minus 1, 0 for, this is for 0, 0, comma 0, 2 pi, comma 0, 4 pi, comma 0, etc. All the even multiples of pi. Or we get the matrix 0, 1, 1, 0, and those are for the odd multiples of pi. So pi, 0, 3 pi, 0, etc. The odd multiples of pi. Let's see what these are. This first one right here, let's write down the characteristic polynomials, minus omega, 1, minus 1, minus omega. The determinant, we get, sorry, not omega, lambda squared minus negative 1 equals 0, lambda squared equals minus 1. So lambda equals plus or minus I. So that's a sinner. Okay. Over here we have minus lambda 1, 1 minus lambda gives us lambda squared minus 1 equals 0. So lambda equals plus or minus 1. All right, that gives you a saddle, right? Lambda is plus 1, things move away from the origin. Lambda is minus 1, things move toward the origin. Let's get the eigenvectors. So we have 0, 1, 1, 0 times xy equals 1 times xy. That gives us y equals x and x equals y. So that gives us an eigenvector of 1, 1 for lambda equals 1. And for lambda equals minus 1, we'll get something similar. We get y equals minus x, which gives us minus 1, 1. All right, let's plot it. For the even multiples of pi, comma 0, even multiples of pi, comma 0, we see a center. And for the odd multiples of pi, comma 0, we see the same saddle. Right? So let's do those first. So we see odd multiples of pi. So we have pi, 3 pi, 5 pi, doing odd multiples of pi, comma 0. And for those, we see, let's see, we have got 1, 1. Here's 1, 1 is an eigenvector that points along the line y equals x at that point. And there we have a positive eigenvalue, so things move away from the origin. And in the opposite direction, minus 1, 1, things move toward the origin. Same exact picture over here. Same exact picture over here. And over here. Oops. Okay. And then for the even multiples of pi, that's these points here, we see center tangencies. Okay, and you can even tell, like near these saddles, things have to be going this way. So these center tangencies are all, looks like to me like they're all going, they've all got to be going clockwise. And then we can kind of start to fill in the rest of the picture here. You know, near these points, we see these hyperbolas. So things probably go something like this. Okay. Things go that way and that way. All right, let me just remind you what the axes are. This first axis is alpha, and this is omega. So alpha is the displacement. It's the angle there. If you look at the picture, the video now, you see the angle here. Alpha is how far I am, and omega is how fast I'm going in that direction, right? My rate of change of angle. So this is actually a cool picture. It's saying that for relatively small values of omega, so I'm in this kind of band here, this range of values, so different color. In this range of values here, or I can even use a highlighter. This range of values here. If omega is small, then I just give it a little kick and it's going to go in circles. Okay, we're not using any friction here. We just go alpha increases and then alpha decreases, and then alpha increases and alpha decreases. And when alpha is biggest, the angular velocity is smallest. And when alpha is smallest, right in the middle, then it's going fast. And then when alpha is the most negative, then we've slowed down to 0 again. So the angle's increasing, the angular velocity is decreasing, and then the angle's decreasing and the angular velocity is increasing in the negative direction. That's exactly these circles here in this picture. It's exactly these circles here in these pictures. Okay. Unless I give it a big enough kick. If I give it a big enough kick, boom, I hit it really hard. And what's going to happen is it's going to go up, 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 slow down, slow down, slow down. And if I give it a big enough kick, it'll just keep going. So the angle is just going to keep increasing, increasing, increasing. If the angular velocity is positive, and positive enough, the angular displacement keeps increasing, increasing, increasing. And that's exactly what's happening here, is that the angle keeps getting bigger. Okay, it speeds up, slows down, speeds up, slows down, speeds up, slows down, but that's the wiggling, but the angle is constantly moving off to the right. And if I give it a kick in the opposite direction, the negative direction, and hard enough, it goes back the other way. And the angle keeps decreasing. And that's exactly what's happening on the bottom of the picture here, is the angle keeps decreasing, going that way. Okay? So I think this is a really cool example because you get some relatively simple physics up here. It's just the trigonometry of this picture. It's not terribly deep physics. We're not doing quantum mechanics here. Okay, and then that gives you this nice, very simple equation here. Okay, we can break up that equation into a system. That's right here, and it's a small, simple system. And then we can do this equilibrium point analysis to get this beautiful picture, which really agrees with what your intuition should be about pendulums. If you give a pendulum a small kick, it just oscillates back and forth. If you give it a big kick, it'll just keep going round and round and round. Okay? So that's kind of a beautiful application of all this. And I encourage you to think about this, review the video, back it up if you need to really understand what's going on here. All right. Hopefully I will be available for office hours tomorrow. And sorry, not tomorrow, Wednesday morning, if you need help Wednesday morning. I don't know if I was available for office hours this morning. You're viewing this on Monday if you're viewing it at all. So email me if you have questions. You've got some web work problems due. Good luck with those. Just give me your best shot and just email me if you have questions, or come to my office hours Wednesday morning. I will be in touch through Sakai, sending messages to the class about my status, about when I'm going to be back in class and when I'll be available for questions. But otherwise, feel free to email me. All right. Hopefully I'll see you all on Wednesday. Bye.